I'm going to start the session on science and society. It's a great privilege to have very distinguished panelists with us. I will take a few minutes to introduce them each, and then I will set the tone for the session. It was great to see how economics impacts society, and we're going to try to see how physics and hard sciences impact society. So with that, let me start with the first speaker, Peter Littlewood. He is my boss's boss. I think that's correct, right, Peter?
Something like that.
Something along the chain where the chain ends, that's where Peter is. So he's a great theoretical physicist, solid-state physicist, some field that I'm also working in. Peter is a graduate from University of Cambridge and then came to the United States to Bell Labs, if I'm not mistaken. And then he went back to University of Cambridge, formed some important institutes there, actually related to nanoscience. And then he went back to this side of the pond, become director of material science or physical sciences, I don't remember. Physical sciences as an associate lab director, and then became the director of Argonne National Lab. He's actually hosting the minister and the Turkish delegation on Monday, so I'm thankful for him on that too. Our next speaker is someone we are very proud of in the Turkish community, Dr. Feryal Ozel. She's indeed an Ozel person. She's an astrophysicist of the highest rank, and when I met her first time in an after-dinner speech about 3 years ago, I said, okay, I found one of my speakers, right? So Feryal is currently a professor of physics at University of Arizona, and she will talk about astrophysics and its impact on the way we perceive universe. The last person also is very special to me because he is my ceramic teacher. And I don't mean the ceramic that you go to the Park District and, shape the ceramic, all right? He is actually a professor of chemical engineering at Princeton University. He was a graduate of Washington University. Then he went to Berkeley for his PhD. And then he worked, I think, short time at Xerox before coming to Middle East Technical University, where our paths crossed. And I'm not going to tell you how long it was ago because most of you were not born then, all right? But nevertheless, I had the privilege of occupying the same building for 5 years. And whatever I learned about the ternary phase diagrams, I actually learned from İlhan Aksay. And then he came back to United States, first to UCLA, then University of Washington, and then ended up at Princeton. He's going to talk about ceramics and materials, how it impacts the society. So here's my idea of how science and society interacts. As we all know, science is an intellectual building process upon an existing body of knowledge. So it connects isolated facts into a coherent and a comprehensive structure. So as such, it's a universal human endeavor. The science we practice here is exactly the same it is practiced in Japan or China. So we find the same results, and if we don't, then we don't trust our results. Science can be, and in fact quite often, controversial. And I don't mean today, I actually mean throughout the history that was the case. We all remember how Socrates drank the poison to defend his ideas. Galileo, the same way, suffered because of his ideas. Darwin was very careful, but nevertheless he delayed his publication for not suffering. And Marx and Nietzsche are still very controversial even today. But the controversies between scientists is very different than controversy between science and the non-scientists. In fact, that particular aspect is not in the domain of science, but really it's in the domain of politics. And a good example of that would be stem cell research in recent times, maybe global warming, where all the scientific facts indicate that it is a problem, but nevertheless it is still debated by the politicians. I'm not going to know, I don't know how Trump thinks about global warming, but I don't think it's very favorable. But also, it need not be political. I mean, earthquake non-prediction ended up some of the scientists in jail in Italy a couple years ago. And diet is a good example. Vaccines, there's a lot of controversy. So these are fields where scientists interact with non-scientists, and unfortunately, they are not really prepared to deal with that. Science can be useful as well as destructive, and a good example of nuclear science, where we benefit from isotopes, cancer therapy, nuclear energy, but it can also be very destructive. So scientific discoveries, on the other hand, have big dividends. So maybe some of our economists may take issue with my next statement, but there was a study done independently in the US as well as in Europe, which indicates that today's world economy, over 60%, relies on quantum mechanics. And that shows itself in the form of communication, in the form of energy, in the form of lightning, in the form of almost everything we do. And therefore, nobody in 1920s, when the quantum mechanics was developed, actually financed it or supported that research to change the world, but it did. In fact, that applies equally to thermodynamics. I mean, the Industrial Revolution and thermodynamics overlapped, and the modern post-industrial revolution coincided with quantum mechanics. And some people argue, what's next? Is it genomics? Is it other fields? But clearly, there's strong interaction between science and society in that regard. The scale of science is something that I wanted to emphasize, is also changing. And its impact on the world economy is growing. And that results in different practices now. For example, for centuries we relied on peer-reviewed publications, which were only accessible by scientists, but now open publishing policies is now dramatically upending the established practices of how science is disseminated in society. So one good example of a debate between scientists, not between scientists and non-scientists, but between scientists, is what is matter and light? Is it particle? Is it... I know your Turkish is pretty good, Peter, so I'm sure you can catch that. But the ones that are in sort of red colored are people who thought matter is waves, all right? Maxwell, Huygens, Aristo. But there are also others who are equally prominent, like Democritus or Alhazen, who thought that they were everything was particles, right? And this debate ended up being resolved with the quantum mechanics, formulation of the quantum mechanics. But science can also be extremely nonlinear. When I came to Argonne, I will tell you, 35 years ago, all right, the best superconductor was niobium-3 tin, right? This was around that, and nothing was changed until then. And we did great things with niobium, titanium, and niobium tin. All the Higgs boson discovery is based on a machine that's built from niobium, titanium. This is temperature of the superconducting transition temperature of the metals. And the established procedure, established ideas was that indeed metal alloys will have to be the answer. But then something dramatically different happened. Oxides were discovered to be superconducting, which were always considered to be insulators. And then boom, this thing went up. And so everybody started synthesizing oxides. And that saturated at some point, and the mechanism for this is still not very well understood. And today, we have a record temperature of about 200 Kelvin in something that nobody even thought of, hydrogen sulfide, all right, under pressure. So scientific thinking is not linear. That's the message that I wanted to give. It can change overnight, but you just don't know when. The scale of modern science is also changed. When Mendel was doing his work in Brünn in Germany on the peas, he was basically working by himself. All right? When Rutherford split the atom and discovered the nucleus, he was working with few individuals like Geiger and Marsden. When the Higgs boson was discovered last year, it was discovered by so many people that I have put here just the people who were their last names starts with A. All right? So you can see that the nature of science has moved from an individual endeavor to a large-scale process. So here's another example very close to my field. This is the first synchrotron or cyclotron Ernest Lawrence made in Berkeley in 1931. Right? And here's what we have at a Large Hadron Collider in Switzerland and France at the border. And we went from 11-inch to 9 kilometer in diameter. All right? So the energy went from few kilo-electron volt to 1 MeV and now to 7 TeV, tera-electron volt. So progress is huge, and the nature of science changes. Here's another example in the area of Feryal, actually. These are some astronomical observatories that started in around the turn of the century, actually. And then it went on to become bigger and more expensive and more people involved, and the more deeper it will see and the more wider wavelength it will see. And our understanding of universe has changed. If you had gone to high school at the time I did and pick up an astronomy book today, you're not going to believe that how little we knew, even in my lifetime when I started education. So astronomy has completely revolutionized itself by building bigger and better instruments. In fact, Hale, who was responsible for the first observatory, wrote a letter in 1928. You're not going to be able to read it, so I will just quote him. "No method of advancing science is so productive as the development of new and more powerful instruments and methods of research. A larger telescope would not only furnish the necessary gain in light space penetration and photographic resolving power, but permit the application of ideas and devices derived chiefly from the recent fundamental advances in physics and chemistry." So we have seen the synthesis of nuclear physics and astrophysics in the form of nuclear astrophysics because we have instruments to actually look at them. If you look at the field that I'm particularly working in, the synchrotron radiation, here are some of the big synchrotron centers that are built around the world. All right? Don't look for Turkey because we're not on the map there yet. All right? But we have one in Jordan that we are building in collaboration with Turkish scientists, Israelis, Iranians, Palestinians working together. And this will start working this year. So if you go across the world, you know, Japan, Germany, Canada, Switzerland, France, England, and so on, Italy, Sweden, the brightest source in the world today, Cornell, and so on. So everybody has built big machines to study proteins, to study matter, to study with X-rays, has built these machines. So in Turkey, we have started a project called Turkish Accelerator Center with the support of Kalkınma Bakanlığı. And this has been going on. This is our dream. This is what we tell them what we want to do. We want to build an accelerator, a neutron source, a free electron laser, some research centers like nanocenters and biology centers and new materials, new energy centers. So this is what we would like to achieve. And our first step towards achieving this goal is this project, TARLA. The acronym is Turkish Accelerator and Radiation Laboratory in Ankara, but it's actually meant to be a fertile TARLA, really, all right? Because we put the seed there. This is what we're building now. It's a 40 MeV superconducting Linacs with 2 undulator beamlines to produce femtosecond infrared radiation. And this project is fully funded now at the Kalkınma Bakanlığı, and we hope to actually be running this in this building in about 2 years. All right. So Turkey has started making investments, but we hope that that will double, triple, and probably go an order of magnitude so that we can actually catch up on this. So without further ado, this is my intention was to bring the issues of science that impacts us here in the US and impacts people in Turkey and how this will relate to society in general. So that's my presentation, and our next speaker is Peter Littlewood. So may I have your computer, Peter?